Very tradition, yeah. So this project is in a larger framework that was the first time I came up to ultrasound data for tendon imaging. So inside the Mind 3D ultrasound project, Jan and Leonard. And what I do, I am interested in inverse problems, so mathematical approach to image formation. And I was thinking about the problem of estimating the trajectory of speckles. And actually you can solve the problem of 3D motion information from a 2D image sequence to such an extent, and I want to explain to you how I see this problem. So what I first received is this nice data that was acquired by Katerina. So it's a high definition sequence of a tendon data. So let's have a look at this. Frame by frame, you see very, very well the sliding. So I just skipped many 16 frames. So you see here normally a very, very, very nice sliding motion of your speckles. And I think that the time dimension is actually bringing you a lot of information. A lot of things are hidden in there, and actually you can extract some information out of plane motion from that. But usually, what you do is just a 2D motion estimation. So whether you use two approaches, you can choose an Eulerian approach or a Lagrangian approach. In the Eulerian approach, you just take fixed observation points, like for example a grid of B-spline basis function for plastic resistation, for example. And then you try to follow the gradient of change in your images, and it gives you local displacement vectors that are uniformly distributed over your imaging plane. Another approach is to use the Lagrangian one. So there you make some detection of speckles, and you will try to track their trajectory over time. And this approach looks more difficult because you have to first detect speckles. So you have to bet on speckles that are good to track. So there is a sequence of two problems that you have to solve. So I try to solve, to keep this Lagrangian approach by solving the two problems at once. So I try a different approach. And it's based on this following characterization. Here you see a line profile to a 2D image. This is, for example, a vertical or horizontal line profile, and you see the intensity, and here you see the time dimension. And if you observe that your intensity do not change for a steady time, that means that the speckle is stationary. If you see quickly the speckle crossing your plane, it will appear and disappear. So there is some motion information in there. And if you see your speckle that is drifting in your 2D plane, then you can get some in-plane motion. You can also have some non-visible speckles actually. So in the vicinity of a reference time, you could estimate in-plane motion and a part of out-of-plane motion as well. So what I will do now is that I will use a statistical representation, Gaussian mixture, to approximate the spatial-temporal data. So I will estimate the joint space and time, model from the 2D+T data. So it looks like this. I start with one big speckles that live in 2D+T, and I will split it to increase image resolution locally. And I will do that with a statistical technique. I keep track also of the hierarchy, so I have a multi-resolution image model that go down to singular speckles. And this gives you a regularized approximation of your image space. So what it looks for the reconstruction, you start fetching data from your dataset, and you estimate the parameters of one Gaussian, then you split it, you get more Gaussians, and you continue fitting them to the data while improving the image definition over time. And at the end, you get a very sparse and continuous image model. So here you see, for example, I have a very few difference you can see between 256 components or 1000. So the complexity of your image do not depend on the number of pixels you have. It depends on the number of visual features you have in your image. And the number of visual features is actually the number of moving speckles. I will will show you some experiments that I connected on the data from Katerina. So here is look, I take a single reference frame from a huge data set. It was 128 frame of 500 to 256 pixels. And here you see the optical flow. That's a cross, you take a line profile and you see the variation over time of intensity. So you can see that if it's horizontal, that means the perspective are steady, and strokes that are a bit slanted means some in-plane motion. And here you see the approximation of this data set with about 8,000 Gaussians. So much less mixture elements than pixels in your input data set. And to each of those image elements, you have an explicit motion vector that is estimated as well. You can extract it from the covariance matrix of your Gaussians. So if you have a zoom, so this is the input data. Here you see the motion information along time. So that's the motion of this horizontal line profile. This is the approximation with here 256 elements. And actually, it's a continuous image model, so you don't have pixels. You can just interpolate continuously and retrieve a continuous intensity field. And also, you have motion vectors for every of your speckles. So what I will do now is that I will want to do a prediction of the motion using this joint-based intensity representation. And for this, you can use the Gaussian mixture regression, so a statistical technique will give you that. And it's how it looks like. For example, if I have here a reference frame, and this is the prediction for an offset of 16 frames, so that's look like this, pretty good match with the reference data. Here is, for example, minus 16 some frames in the past and some frame in the future. Here is plus 32 frames, and there you don't get a good match when you make a prediction far from your reference time, because you get attracted to this kind of cluster, and you get kind of clustering and sparsity. So the model of prediction of motion is kind of valid in the vicinity of your reference time. That's what I want to symbolize that. And then lastly, I also made some quantitative measurements of the motion accuracy. So for this I took, for example, a line profile in black. It's a reconstruction of our approximate model. The gray shadow is the reference image, the conscious data. And you take a speckle, and then you see where this speckle will be predicted to move after 32 frames, and you get this displacement vector. So actually, this is a sub-pixel accurate motion estimate. So in conclusion, so what I tried is another approach to speckle tracking, where I solved two successive problems of speckle detection and tracking at once. And I do that by representing the data as a joint and continuous spatial-temporal Gaussian mixture model. And from the Gaussian mixture model, you can use regression to retrieve your motion information. So basically, from an input that is can be a very large data set of 2D frames without motion information, you can strike a single representation with explicit speckle motion, at least local linear trajectories in that case. Thank you for your attention.